So in a lot of ways, this last section of Chapter 8 is like the reverse of the previous section. It's still about a connection between electricity and magnetism, but it's sort of backwards. It's called electromagnetic induction, and it's a way of making an electric current using a magnetic field. In our last section, we were talking about making a magnetic field using an electric current. This phenomenon of electromagnetic induction is useful in lots of different ways. It's used to power electric generators. It's used in something called a transformer, and it can be used to make a simple microphone. There are also many other devices that use this idea. Electromagnetic induction was discovered by Michael Faraday, a British scientist, who realized that by moving a magnet next to a coil of wire, he could produce a current in that wire. Now there's no battery here, there's no obvious source of electrical energy, but if you move that magnet next to that coil of wire, if you move it fast enough, you can actually make the light bulb light up, and that's proof that there is a current flowing in that wire. Electromagnetic induction can be stated simply as a changing magnetic field produces an electric current. Just a magnetic field won't. If you just set that magnet next to the coil and wait, nothing will happen. You have to move the magnet. You have to change the magnetic field in order to produce the electrical current. So please keep that in mind as we move through this stuff. This electrical current is really caused by something called the Lorentz force. In this diagram here, the green lines represent a magnetic field, and this is a proton, this red thing, moving to the right. And in this situation, the proton would feel a force towards us. All charged particles, like protons and electrons, if they move through a magnetic field, will feel a force like that. To figure out which direction the force is in, it's kind of complicated. It's another right-hand rule. It's called the second right-hand rule, and it actually only works with your right hand for positive charges, works with your left hand for negative charges. But the way it works is, if you hold your hand out, palm up, and you raise your middle finger toward up, that represents the direction of the magnetic field. Your index finger points in the direction of the motion of the proton, and then your thumb will tell you which way the force will be. So the three directions are always at right angles like that. I'm not going to hold you responsible for that. I just thought it was kind of interesting. Okay, so one of the most important applications of this is an electric generator. And your book can draw this much better than I can. You can see in this diagram that there's mechanical energy going in. The person is turning this crank. And because the crank is attached to a coil of wire at the end there, and that coil is in a magnet, when you move the coil, you're actually changing the magnetic field that that coil experiences. Because that coil of wire is experiencing a changing magnetic field from that permanent magnet, there's going to be a current induced in that coil. Okay, so a coil that sees a changing magnetic field will get a current in it, and then they're using that current to power the light bulb. This diagram is showing you the direction of electron flow, which is the opposite to the direction of the current. Anyway, an electric generator is a really, really useful thing, and it's all powered by electromagnetic induction. Basically, all power plants, whether they use fossil fuels, wind energy, hydroelectric power, etc., basically all of them use this idea, this generator idea. And the idea is to turn kinetic energy into electrical energy. It's the opposite of an electric motor, right? In an electric motor, we turned electrical energy into kinetic energy. Anyway, the wind, the water, or the steam that's heated by the burning of fossil fuels, or whatever it is, causes something to turn, right? And that turning turbine is always attached to a coil of wire, which is next to a magnet. And if you turn the coil of wire and hold the magnet still, or if you turn the magnet and hold the wire still, either way, you'll create a current in that wire because the wire coil will be experiencing a changing magnetic field. So that is the secret to how we produce electric power in the world. We just turn a coil of wire next to a magnetic field. So if you're ever out of a job and you want something useful to do, you can always just turn a coil of wire next to a magnet and produce electricity. Your book has this nice page, you can't really see it very well here, but it compares and contrasts an electric motor and a generator. And the main thing here is that, like I said, an electric motor, you put electric energy in a battery or a plug in the wall, and it produces mechanical or kinetic energy. It makes something move. Whereas a generator is the opposite. You put mechanical or kinetic energy in, You turn a turbine somehow, and it produces electrical energy. In both situations, you have to worry about changing the direction of the current to keep the cycle going. And so we need to talk about two different kinds of current now, what's called AC and DC. Because if you don't make a trick with the connections in a generator, what you actually generate is a current that changes directions, and that's known as an alternating current. AC/DC, it's not the rock band. AC means alternating current, and DC means direct current. And as the names would suggest, direct current is a steady current. It goes just in one direction and it doesn't change. It's the kind of current that's produced in a battery. AC, alternating current, is not steady at all. It's constantly changing. This graph that looks like a wave represents AC, or alternating current. The current not only changes strength, but it constantly changes direction, going one way and then reversing, and then back and forth and back and forth. And it's the kind of current that you would get when you plug something into the wall. And it's also the kind of current that's produced by many electric generators. Now, it seems kind of annoying to have alternating current, but it's actually very useful. One reason why it's so useful is because it's the only kind of current that can be used with what's called a transformer. Transformer. In a transformer, a strange and magical thing happens. A current passes in through one coil of wire on the left, that black squiggly thing, and then it's not connected to the wire on the other end, the coil of wire on the right side, the squiggle on the right side. But somehow the current on the left causes a current in the coil on the right, even though they're not touching. Normally, an open circuit, a hole in the circuit like this, would never let current pass. But this is a special device, and through a trick we're going to learn in just a minute, a transformer actually does let a current in the left produce a current in the right, even though the current doesn't directly flow between them. So what happens is, if we pass a current through the wire on the left, through the coil on the left side, that's called the primary coil, what's it going to do? Well, we learned in the last section that it's going to produce a magnetic field all around that coil, right? And that's going to look like this. The green lines are representing the magnetic field produced by the primary coil on the left, and the red arrows indicate that there's a current flowing there. Okay, well, if we have a current flowing and we have a magnetic field, and if we can make that current change, then the magnetic field will change, and the coil on the right is now in position to get its own current. Because any coil that sees a changing magnetic field is going to have a current induced in it. That's electromagnetic induction. So a transformer works by having two coils, and in order to have the current in the first coil change, so that we can have a changing magnetic field, we need something like alternating current. So here you can see the current induced in the second coil, the secondary coil. So that's how a transformer works. The current doesn't pass directly from the primary to the secondary, but the current in the primary causes a magnetic field, and if we change the current, then the magnetic field changes, and the changing magnetic field experienced by the secondary coil produces a current in the secondary coil. That's pretty cool, but it's just a trick. Why would we want to do that? Why not just connect the wires and not mess around with all this magnetic field stuff? Well, like I said, this only works with a changing or alternating current. But why we might want to use a transformer is to step up or step down the voltage. Now, what the heck does that mean? Tune into part 2 of this section to find out what transformers are good for and how this all fits in with you turning on the light to do your homework.